we want to understand now our observables. So we said these are observables. So can we observe them? Can we have a state in which we say what is the value of Lx, the value of Ly, and the value of Lz? Well, a little caution is necessary because we had states and we have position and momentum operator, and they didn't commute, and we ended up that we could not tell simultaneously the position and the momentum of a state. So for these angular momentum operators, they don't commute, so a similar situation may be happening. So I want to explain, for example, or ask, can we have simultaneous eigenstates, of Lx, Ly, and Lz. And the answer is no. And let's see why that happens. So let's assume we can have simultaneous eigenstates. And let's assume, for example, that Lx on that eigenstate phi naught is some number lambda x phi naught, and Ly on phi naught is equal to lambda y phi naught. Well, the difficulty with this is essentially, well, we could even say that Lz on phi naught is equal to lambda z phi naught. So what is the complication? The complication are those commutators. If you do Lx, Ly on phi naught, you're supposed to get I h bar Lz on phi naught. And therefore, you're supposed to get I h bar lambda z times phi naught, because it's supposed to be an eigenstate. But how about the left-hand side? The left-hand side is Lx, Ly on phi naught minus Ly, Lx on phi naught. When Ly acts, it produces a lambda y, but then phi naught. And then when Lx acts, it produces a lambda x. So this produces lambda x, lambda y, phi naught, minus lambda y, lambda x, phi naught, which is the same thing. So the left-hand side is 0. 0 is equal to lambda z phi naught. So you get that lambda z must be 0. If you have a non-trivial state, lambda z should be 0. By the other commutators, this commutator applied to phi naught would be 0 again, because each term produces a number and the order doesn't matter. But then it would show that lambda x is 0. And this would show that lambda y is 0. So at the end of the day, if these three things hold, then all of them are 0. Lambda x equal lambda y equal lambda z equals 0. So you can have something that is killed by all of the operators, but you cannot have a non-trivial state with non-trivial eigenvalues of these things. So we cannot tell what is Lx on the state and Ly on the state simultaneously. Any of those two is too much. So if we can't tell that, what can we tell? So what is the most we can tell about the state is our question now. We can tell maybe what is its value of Lx, but then Ly and Lz are undetermined. Or we can tell what is Lz, and then Lx and Ly are undetermined, uncalculable, impossible in principle to calculate them. So let's see what we can do. And the answer comes from a rather surprising thing. The fact that if you think about what could commute with Lx, Ly, Lz, it should be a rotationally invariant thing, because Lx, Ly, and Lz do rotations. So the only thing that could possibly commute with this thing is something that is rotationally invariant. Yes. The thing that could work out is something that is invariant under rotations. Now, we said, for example, the magnitude of the vector r is invariant under rotations. You rotate the vector, but the magnitude is invariant. So we can try the operator L squared, which is proportional to the magnitude squared. So we define it to be Lx, Lx, plus Ly, Ly, plus Lz, Lz. And we try it. We try to see if maybe Lx commutes with L squared. Remember, we had a role for L squared in this differential operator that had the Laplacian, the angular part of the Laplacian was our role for L squared. So L squared is starting to come back. So let's see here. This is Lx. Now, I'll write the whole thing. Lx, Lx, plus Ly, Ly, plus Lz, Lz. Now, Lx and Lx commute, so I don't have to bother with this thing. That's 0. But the other ones don't commute. So let's do the distributive law. So this would be an Lx, Ly, Ly, plus Ly, Lx, Ly. This is from the first. Plus Lx, Lz, Lz, plus Lz, Lx, Lz. And if you don't put these operators in the right order, you don't get the right answer. So I think I did. Yes. It's correct. Now you use the commutators and hope for the best. So Lx, Ly is IH bar Lz, Ly. Lx, Ly is plus IH bar Ly, Lz. So far, no signs of canceling. These two things are very different from each other. They don't even appear with a minus sign, so this is not a commutator. But anyway, what is this? Lx with Lz. Well, you should always think cyclically. Lz with Lx is IH bar, so this would be minus IH bar Ly, Lz. And this is again, Lz with Lx would have been IH bar Ly, so this is minus IH bar Lz, Ly, and it better cancel. Yes. This term cancels with the first, and this term cancels with this, and you get 0. That's an incredible relief. because now you have a second operator that is measurable simultaneously. You can get eigenstates that are eigenstate of one of the L's, for example, Lx, and L squared, because they commute. And you won't have the problems you have there. In fact, it's a general theorem of linear algebra that we'll see a little bit of that in this course, and you'll see it more completely in 805, that if you have two Hermitian operators that commute, you can find simultaneous eigenstates of both operators. Mean eigenstates that are eigenstates of one and eigenstates of the second. Simultaneous eigenstates are possible. So we can find simultaneous eigenstates of these operators, and in fact, you could find simultaneous eigenstates of Lx and L squared, but given the cyclicity of all this, it also means that Ly commutes with L squared, and that Lz also commutes with L squared. So you have a choice. You can choose Lx, Ly, or Lz, and L squared, and try to form simultaneous eigenstates from all these operators. Two of them. Let's study those operators as differential operators a little bit. So x, y, and z are your spherical coordinates, and they are r sine theta cos phi, r sine theta sine phi, and r cos theta. We're trying to calculate the differential operators associated with angular momentum using spherical coordinates. So r is x squared plus y squared plus z squared. Theta is cosine minus 1 of z over r, and phi is tan minus 1 y over z. And there's something very nice about one angular momentum operator in spherical coordinates. There's only one angular momentum that is very simple. It's rotations about z. Rotations about z don't change the angle theta of spherical coordinates, just change the angle phi. R doesn't change. The other rotation about x, messes up phi and theta, and all the others are complicated. So maybe we can have some luck and understand what is dd phi, the dd phi operator. Well, the dd phi operator is dy d phi plus ddx dx d phi, rules of chain rule for partial derivatives, plus ddz dz d phi. But z doesn't depend on phi. On the other hand, dy d phi is what? Dy d phi, this becomes a cos phi, it's x. X ddy. And the x d phi is minus y. And you say, wow, x ddy is like x py minus y px. That's the z component of angular momentum. So indeed, Lz, which is h bar over I, x ddy minus y ddx, H bar over I is because of the p's, x py minus y px. And this thing is d d phi, so LZ you've discovered is just H bar over I d d phi. A very nice intuition that tells you that the angular momentum in the z direction is associated with this operator. So I have left as exercises to calculate the other operators that are more messy, and to calculate Lx, Ly, as well in terms of dd thetas and dd phis. And as you remember, angular momentum has units of h bar, and angles have no units, so the units are good, and we should find that. So that calculation is left as an exercise, but now you probably could believe that L squared, which is Lx, Lx plus Ly, Ly plus Lz, Lz, is really minus h squared 1 over sine theta dd theta. No, it's not 1 over sine theta. Yeah, 1 over sine theta dd theta. Sine theta dd theta plus 1 over sine squared theta d second d phi squared. So the claim that I had relating the angular momentum operator to the Laplacian is true, but you now see the beginning of how you calculate these things, but it will be a simple and nice exercise for you to do it.